Hello, everyone. In this section, we will introduce the characteristic equations of bipolar junction transistors, or BJT devices. In the previous section, we discussed the voltage and current mechanisms of BJT devices operating in active mode. In this section, we will derive the current and voltage equations based on those operating mechanisms. We first start from the collector current, IC. As mentioned earlier, IC mainly comes from carriers injected from the emitter into the base, then diffusing across the base and being collected by the collector. Therefore, IC is essentially a diffusion current in the base region. Since diffusion current is determined by the concentration gradient of the diffusing carriers, we first need to find that concentration gradient. At the edge of the base region near the emitter, the electron concentration, Np at xp, equals Np0 multiplied by the exponential of Q times VBE over KT. Here, the whole ratio Q times VBE divided by KT is inside the exponential term. At the edge near the collector, the electron concentration is approximately 0. Therefore, the electron concentration gradient across the base is approximately negative Np at xp divided by Wb. The electron diffusion current flowing toward the collector is then AEBJ times Q times dN times this concentration gradient. The negative sign indicates that the current direction is to the left. Wb is the neutral base width, which is the total base width after subtracting the depletion region widths of the two PN junctions. After substituting Np at xp into the equation, the electron current becomes negative AEBJ times Q times dN times Np0 divided by Wb multiplied by the exponential of Q times VBE over KT. We then define the bias-independent coefficient as Is, where Is equals AEBJ times Q times dN times Np0 divided by Wb. Under thermal equilibrium, Np0 equals Ni squared divided by the base doping concentration, Na. Therefore, Is is proportional to Ni squared. As introduced in the semiconductor chapter, Ni squared is a strong function of temperature, so Is is also strongly temperature dependent. As temperature increases, Is also increases. Finally, the diffusion electron current in the base region is negative Is multiplied by the exponential of Q times VBE over KT. In terms of the collector terminal current direction, the collector current IC has the magnitude Is multiplied by that same exponential term. The key result is that the collector current IC equals Is multiplied by the exponential of Q times VBE over KT. The collector current flows into the collector terminal. Its value is controlled by the base emitter junction voltage, VBE, and is ideally independent of the base collector junction voltage, VCB. Since Is is proportional to Ni squared, IC is also strongly temperature dependent and increases as temperature rises. This shows the basic operation of a BJT. The voltage between two terminals, the base and the emitter, controls the current at the third terminal, the collector. Next, we introduce the equation for the base current, IB. As described earlier, IB has two components. The first component is the whole current injected from the base into the emitter under forward bias of the BE junction. The second component is the recombination current caused by electrons injected from the emitter into the base. As these electrons diffuse toward the collector, a small portion recombines with holes in the base. We first calculate the whole current injected from the base into the emitter. Based on the current equation derived in the previous PN junction chapter, this whole current, IPE, equals the junction area AEBJ multiplied by Q, the whole diffusion constant dP, and PN0, divided by the whole diffusion length LP, and then multiplied by the exponential of Q times VBE over KT. Again, Q times VBE divided by KT is inside the exponential term. The negative sign indicates that the current direction is to the left. From the figure on the right, this current flows into the base terminal. Next is the recombination current component. The recombination current, IPRE, equals the total number of excess electrons stored in the base region divided by the electron lifetime, tau b, which is the average time before those electrons recombine. The total stored electron charge, Qn, is obtained by integrating the charge distribution over position. Since the distribution is approximately triangular, Qn equals the junction area, AEBJ times Q times Np at xp times Wb divided by 2. Equivalently, it can be written as AEBJ times Q times Wb times Ni squared divided by 2Na multiplied by the exponential of Q times VBE over KT. This recombination current flows into the base terminal. Physically, electrons vanish through recombination in the base, and holes must be supplied from the base terminal to support that recombination. The total base current IB is the sum of these two current components, and both components flow into the base terminal. Therefore, IB equals IPE plus IPRE. After rearranging the expression, we can factor out IS and the same exponential bias term as shown in the equation on the slide. Therefore, the base current equation can be written as IB equals IS multiplied by the exponential of Q times VBE over KT multiplied by a constant factor. The red part of the equation is the collector current IC that we just derived. Therefore, IB equals IC times a constant factor. We define this constant factor as 1 over beta, so IB equals IC divided by beta. In general, beta can be as large as about 50 to 270, which means the collector current can be more than 100 times larger than the base current. If IB is considered the input current signal and IC is the output current signal, then the BJT can amplify the current signal by a factor of beta. Therefore, to increase the current gain, we need to increase beta. From the beta expression, a larger beta requires a narrower base width, WB, a lightly doped base with lower NA, and a heavily doped emitter with higher ND. This is why the emitter is usually the most heavily doped region inside a BJT. Finally, we introduce the emitter current, IE. For a three-terminal device, the total current flowing into the device must equal the total current flowing out of the device. In this NPN current convention, the currents entering the device are IB and IC, and the current leaving the device is IE. Therefore, IE equals IB plus IC, so IE equals IB plus IC. Since IB equals IC divided by beta, we can substitute this relation back into the equation to derive the relationship between IE and IC. After substitution, IE equals IC divided by beta plus IC. This can be rewritten as IC multiplied by the quantity 1 over beta plus 1, or IC multiplied by 1 plus beta divided by beta. Rearranging the equation gives IC equals beta over 1 plus beta, multiplied by IE. We define beta over 1 plus beta as alpha. Therefore, IC equals alpha times IE. Since beta is usually much larger than 1, alpha is slightly less than 1, but very close to 1. For example, if beta equals 100, then alpha is a 0.99. This means IC and IE are almost the same, with IC only slightly smaller than IE. We can also start from IE equals IB plus IC and derive the inverse relationship between alpha and beta. The result is beta equals alpha divided by 1 minus alpha. Therefore, once alpha is known, beta can be calculated, and conversely, once beta is known, alpha can also be calculated. To summarize the three-terminal current relationships of an NPN BJT, IE equals IB plus IC. Also, IC equals beta times IB, and IC equals alpha times IE. The two gain parameters are related by alpha equals beta divided by 1 plus beta, and beta equals alpha divided by 1 minus alpha. If the emitter and collector terminals are accidentally interchanged, the BJT operates in reverse active mode. Because a real BJT is not symmetrically doped, this operation is very different from normal active mode. To achieve high current gain, the emitter doping concentration must be much higher than the base doping concentration, and the base doping concentration is much higher than the collector doping concentration. Therefore, in reverse active mode, the reverse current gain beta R is usually below 1, roughly from 0.01 to 1. The reverse alpha R, is also much smaller than 1, roughly from 0.01 to 0.5. The key current mechanism and equations for an NPN BJT are summarized on the slide. The main emitter and collector currents come from the forward-biased BE junction. When the device operates at a relatively high conduction current, the BE junction forward voltage can be approximated by the constant voltage drop model, so VBE is usually taken as about 0.7 volts. This approximation makes DC circuit analysis much faster. After deriving the current voltage equations and the three-terminal current relationships for NPN BJT devices, we can apply the same mechanism to PNP BJT devices. As described in the previous section, the operating principle is the same. The difference is the carrier type and therefore the current direction. For a PNP device, the collector current equation is still IC equals IS multiplied by the exponential of Q times VEB over KT. Here, VEB is the forward bias voltage of the BE junction. Since the emitter is p-type, its potential must be higher than the base potential for forward bias, so VEB is positive and can be approximated as 0.7 volts for quick DC analysis. The current relationships are the same as in the NPN case. IE equals IB plus IC equals beta times IB, and IC equals alpha times IE. The only difference is that the current directions are reversed. For a PNP BJT, IE flows into the terminal, while IB and IC flow out of the terminals. After introducing the current relationships of an NPN BJT, we now look at its circuit symbol. In an NPN BJT, the emitter, base, and collector regions are doped as N-type, P-type, and N-type respectively. In active mode, the base emitter junction must be forward biased, so the base voltage, VB, must be higher than the emitter voltage, VE. The base collector junction is usually reverse biased, so the collector voltage, VC, must be higher than the base voltage, VB. Therefore, in normal active mode operation, VC is greater than VB, and VB is greater than VE. Circuit symbols are usually drawn with the higher potential terminal on top, so the collector is placed at the top and the emitter at the bottom. The conventional current also follows this direction. For an NPN BJT, IC and IB flow into the device, while IE flows out of the device. Because a BJT is not a symmetric device, an arrow is added at the connection between the emitter and the base to identify the emitter terminal. The arrow direction also indicates the direction of the conventional emitter current. Finally, we summarize the collector current equation and the three terminal current relationships for an NPN BJT. The term KT divided by Q is called the thermal voltage, and it can be written as VT. At a temperature of 300 K, the thermal voltage is about 25.9 millivolts. After summarizing the NPN case, we can directly extend the same ideas to a PNP BJT. As shown in red on the slide, the doping types are opposite to the NPN case. For the BE junction to be forward biased, VE must be greater than VB. For the CB junction to be reverse biased, VB must be greater than VC. Therefore, for a PNP BJT in active mode, the voltage relation is VE greater than VB and VB greater than VC. Since the emitter has the highest potential, it is usually drawn at the top of the circuit symbol. Again, the arrow at the BE junction identifies the emitter and indicates the conventional current direction. We have already introduced the current and voltage characteristics of NP-NB-JT devices in active mode, discussed reverse active mode, and noted that cutoff mode occurs when both PN junctions are reverse biased, so no significant current flows. Next, we look at the last operating mode, saturation mode. The question is how an NP-NB-JT in saturation mode differs from one in active mode. First, consider the bias conditions for saturation mode. The BE junction is forward biased, just as in active mode. However, the BC junction is also forward biased, which is the key difference from active mode. Since PN junction current is strongly related to the carrier concentration distribution inside the semiconductor, we first compare the BC junction under reverse bias and forward bias. The diagrams on the right show the carrier concentration profiles of the BC junction under reverse bias and forward bias. We focus on the minority carrier distributions in the neutral base and collector regions. When the BC junction is reverse biased, the minority carrier concentrations near both sides of the depletion region decrease exponentially and become almost zero. When the bias becomes forward bias, these concentrations increase exponentially. In the base region, the electron concentration profile becomes less steep. This reduced concentration gradient in the base lowers the diffusion current. As a result, the electron current injected from the emitter decreases as it passes through the base, and fewer electrons are eventually injected into the collector. Therefore, IC decreases. In addition, because the minority carrier concentration in the base increases, more injected electrons recombine with holes in the base. This increases the recombination current and therefore increases the base current, IB. In the collector region, the reverse bias hole diffusion current was originally so small that it could be ignored. Under forward bias, however, this hole diffusion current increases significantly. its current direction is out of the collector terminal, opposite to the electron current injected from the base into the collector. Therefore, this increased hole diffusion current reduces the total collector current, IC. In summary, when a BJT operates in saturation mode, IB increases while IC decreases. Therefore, the current gain, beta equals IC divided by IB, decreases. In saturation mode, this beta is called forced beta, and it is much smaller than the beta in active mode. Physically, this reduction in current gain mainly comes from the increase in minority carrier concentration caused by forward bias of the BC junction. If the BC junction forward bias is still below 0.4 volts, the effect is small and the device can still be analyzed as active mode. Once the BC junction forward bias exceeds 0.4 volts, the device enters saturation mode. In this region, beta is low and changes with bias, unlike active mode where beta is nearly constant. Finally, we summarize the bias condition for an NPN BJT in saturation mode. The BE junction must conduct with a large forward current, so VBE can be approximated as 0.7 volts using the constant voltage drop model. The BC junction must also be forward biased by more than about 0.4 volts, so VBC is greater than 0.4 volts. The collector emitter voltage is VCE equals VC minus VE, which can also be written as VBE minus VBC. Therefore, VCE is approximately 0.7 volts minus VBC. Since VBC is greater than 0.4 volts in saturation, VCE becomes less than about 0.3 volts. Therefore, in practice, we usually check whether an NPN BJT is in saturation mode by looking at VCE. Once the device enters saturation mode, VCE can be approximated as 0.2 volts for fast DC circuit analysis. This constant voltage approximation usually gives acceptable error. By the same reasoning, for a PNP transistor in saturation mode, the BE junction is forward biased and can be approximated by VEB equal to about 0.7 volts. The BC junction must also be forward biased by more than about 0.4 volts, so VCB is greater than 0.4 volts. Therefore, when the emitter collector voltage VEC is within about 0.3 volts, the PNP BJT is in saturation mode. Once it enters saturation, VEC can be approximated as 0.2 volts for fast DC circuit analysis. Lastly, let's look at the IC versus VCE characteristic curve of an NPN BJT. In active mode, VCE is greater than 0.3 volts. The collector current is IS multiplied by the exponential of VBE over VT, where the ratio VBE over VT is inside the exponential term. Also, IC equals beta times IB and equals alpha times IE. In this region, beta is approximately constant. Therefore, IC depends mainly on VBE and is ideally independent of VCE, as shown in the curve. Once VCE becomes smaller than about 0.3 volts, IC decreases significantly because the BC junction becomes forward biased. The lower VCE becomes, the smaller IC becomes, as shown in the figure. In this region, the forced beta is low and is not a constant. This concludes the introduction to the characteristic equations of bipolar junction transistors, or BJT devices. Please look forward to the next lecture. See you next time. Bye.